Hello everyone, welcome to this lecture. So, in this lecture we will see an example of a computation where we can do the circuit evaluation in the mixed world by using the ABY conversions, and the computation that we will take is that of performing modular exponentiation. Okay. So, participants who are familiar with the square and multiply trick, they will know that if we want to compute a to the power x mod n, okay, where a is the base, x is the exponent and n is the modulus, then we do not do the following. We do not multiply a x minus 1 times and do mod. We do not do this because this requires exponential amount of time. Rather we perform we compute a to the power x modulo n by using the square and multiply trick. And what do we do in the square and multiply trick? We basically focus on the bit representation of exponent x. Okay. So, suppose the bits of x are x of 0, x of 1 all the way to x of L minus 1, and what we do is in each step we square the current power of the base. So, we start with a power 1, then we compute a square, then we compute, if we multiply a square with a square we get a power 4, if we square it we get a power 8. We keep on doing this step in each iteration, and in each iteration we also check whether the current bit of the exponent of x is 0 or 1. If it is 1, then whatever partial result we have computed till now, partial result means our eventual goal is to compute a power x. So, we will compute it step by step and accumulate the required powers of a to get this a power x done. So, if the current bit of x is 1, then we have to accumulate the current power of a that we are considering. So, to demonstrate it, suppose we want to compute a to the power 53 modulo n, then 53 is my exponent whose bit representation from LSB to MSB is this, and a to the power 53 can be written as a to the power 1 multiplied with a power 4 multiplied with a power 16 multiplied with a power 32. Okay. So, as I said in the algorithm, what we do is in each iteration we go from the next power a to the current power a to the next higher power of a, where the next higher power of a is obtained by squaring the current power of a. Okay. And then we have to identify which powers of a we have to accumulate and which powers of a we have to ignore, right. And the powers of a which we are accumulating, they will be stored in a intermediate result y, and once we have accumulated all the required powers of a, we have the final result ready in y. So, depending upon the bits of a from LSB to MSB, we can identify which powers of a we have to consider, which powers of a we have to ignore. Say for instance, we have the LSB of x is 1. So, we have to take a power 1, then the next bit is 0. So, ignore a square, the next bit is 1. So, we have to accumulate a power 4 and so on. Okay. So, that is the way we can compute a power x modulo n, and this will not require you to perform 52 multiplications, right. So, one way of computing a power 53 modulo n will be you multiply a itself 52 with itself 52 times and then take modulo n, but instead we can actually we can compute a to the power 53 modulo n here by computing 1, 2, 3, 4, 5 and 6, 7, 8, 9 multiplications. Okay. Okay. So, we can save exponential amount of computation here, and that is why this square and multiply trick is a very nice trick to compute a to the power x modulo n. So, now what we want to do here is the following. Imagine that Alice and Bob here wants to compute a to the power x modulo n, but none of these two parties know the value of a, the value of x, the value of mod n. So, the base a is arithmetic secret shared between these two parties, namely Alice has an L bit share, Bob has an L bit share, such that if we add those L bit shares we get the base a, whereas say the bits of the exponent, they are Boolean secret shared between Alice and Bob. Okay. So, you can see here that we are not letting x to be arithmetic secret shared between Alice and Bob, because in the square and multiply trick in each iteration Alice and Bob requires the bit representation of x, not the full x. So, that is why we can imagine that instead of x being secret shared between Alice and Bob, it is the bits of x which are secret shared between Alice and Bob, and say for instance the bits of x are secret shared between Alice and Bob as per the GMW Boolean representation, namely for each of these bits x naught, x 1, x l minus 1, Alice has a random bit share Boolean share and Bob has a random Boolean share. So, that such that if we XOR them we get the bits of x, and say the bits of n as well are secret shared between Alice and Bob, but say according to the Yau representation. Okay. Now, our goal is to design a protocol which allows Alice and Bob to interact and let them learn the output y in a secret shared fashion, where the output y is now going to be available in arithmetic representation. Okay. That is what is the example computation that we are considering. So, you can imagine that the function that they are interested to compute is a power x modulo n, where all the inputs a, x and n are secret shared, but in different notations, different representations. The base a is arithmetic secret shared, the bits of exponent are Boolean secret shared as per the GMW notation, and the bits of the modulus n is also secret shared as per the Yau's representation, and we want Alice and Bob to get the final output y in the arithmetic secret shared representation. Okay, that is the goal. Now, to get this computation done, we will identify the building blocks that we will require here. So, definitely if basically we have to evaluate, we have to run the square and multiply algorithm, but on secret shared values, and in the square and multiply method we have to do modular multiplications, okay, because there are two instances of multiplication, one when we are computing the next power of a by squaring the current power of a, and another conditional multiplication where we are conditionally updating the partial result. By the way, both these multiplications are modulo n. I have not written it out explicitly, but both these multiplications are modulo n. So, we have to imagine that we have to consider a mod circuit which takes the bits of the mod n as per the Yau's representation, and the value v whose bits are represented as per the Yau representation, and the output of this circuit will be the value of v modulo n as per the Yau's representation. Namely, the entire value v will not be secret shared, but rather the entire value z will not be secret shared, but it will be rather the bits of z which will be secret shared as per the Yau's representation. So, this will be a circuit which will be used or which will be evaluated to get this computation done. Why so? Because as I said here, we require modular multiplications to be performed here, and modular multiplications means we have to basically compute mod n Okay. So, this y times z, you can imagine that this is a value. So, we have to compute call it as suppose y is y multiplied with z is a, then we have to compute a modulo n, and z multiplied with z is say b, we have to compute b modulo n. So, there are two steps where we have to perform mod of a value with respect to n. So, that is why wherever we need to do or wherever we need to compute the value of some number v modulo n, we will invoke this mod circuit, okay, which will ensure that neither the mod is revealed nor the value which is whose mod is computed is revealed, and also the result of this computation is also not revealed. Everything will be done in a secret shared fashion. Okay. So, we can imagine that okay, whatever is the mod circuit is basically you can compute the mod v modulo n based on a division method or the repeated subtraction method. So, whatever is that circuit's logic is here, that is a Boolean circuit, and that circuit can be evaluated as per the Yau's protocol. We will also invoke a multiplication circuit which will take two values, two inputs in arithmetic secret shared fashion and the bits of mod n in the Yau representation, and it produces the result E, which is the product of the input C and D modulo n. Okay. And again everything is going to happen in secret shared fashion, but now you can see that the input C and D are going to be available in arithmetic secret shared fashion, and the mod n will be made available in Yau secret shared fashion, and the output that we desire here is in arithmetic secret shared fashion. Okay. Where exactly this mult circuit will be invoked? So, if we go here when we are going to perform y into z, that mult circuit will be invoked, and whenever we have z into z, we are going to invoke this mult circuit, and then after that we have a mod n operation. So, to get the effect of mod n done, we will go and evaluate the mod circuit, but then that will require a switching operation. Why? Because when we perform this mult operation, it will produce us the result E in the arithmetic representation, and we have to then compute E modulo n. Okay. So, E, you can imagine that we will be first computing C times D, that will be the multiplication circuit here. Now, whatever is C times D, we have to reduce it modulo n. To reduce that value C times D modulo n, we have to take the help of this mod circuit, but this mod circuit expects the input in Yau's representation, but C times D we have computed the intermediate result C times D we have computed in the arithmetic representation. That arithmetic representation has to be converted into Yau's representation, and then that C times D will be reduced modulo n, and then we will come back to this arithmetic PERT by doing a Yau to arithmetic conversion, and that will give us the value C times D modulo n. Okay. And then we will also require a multiplexer circuit, okay, and the logic for this multiplication circuit will be the following. It will take two inputs C and D in the arithmetic representation and a bit B in the Boolean secret shared representation, and depending upon whether this selection bit B is 0 or 1, it produces either the output C or the output D in the arithmetic representation. So, that is the logic of this mux circuit, and where exactly this mux circuit will be invoked while securely evaluating the square and multiply circuit. So, if in each iteration we check the current bit of x, if the current bit of x is 0, then we do not accumulate the current power of A, whereas if it is 1, then we accumulate the current power of A, right. So, that logic can be instantiated using a mux circuit, but now the bits of x will not be available in clear, but rather in secret shared fashion. To model it, we are ensuring here that the selection bit which determines whether you take C as the output or D as the output is secret shared, and the inputs also which you have to select as possible outcomes are also secret shared. Okay. And now you can imagine that by plugging in these three components, this MOT circuit, this MULT circuit and this MUX circuit, Alice and Bob can evaluate a to the power x modulo n in a secret shared fashion. In each iteration they have to do a MULT followed by mod. So, they have to do this conversions here, and then they have to evaluate a MUX circuit and accordingly decide whether to change the partial result or not change the partial result, and the partial results will keep on getting accumulated and finally the result will be available in a arithmetic secret shared fashion to Alice and Bob. So, now you can see that how the entire computation can be done in mixed world instead of computing a power x modulo n entirely as per the Yau's protocol or entirely as per the GMW protocol. We can do different parts of the computation in different representation with the help of this switching mechanisms. So, with that I end the discussion on the ABY conversions. As I said, all the discussion related to the ABY conversions are from the original paper, but recently more efficient conversions for the two party case are proposed in this new paper, and we have the conversions between ABY world for the 3 party case, 4 party case and so on. Okay. So, this mixed world computation for a small number of parties is a very active area of research, because remember we saw good practical motivation for studying mixed world computation for a small number of parties, and specifically in the context of privacy preserving machine learning, doing machine learning computations using in a privacy preserving fashion using MPC techniques for a small number of parties is a very active area of research. You can see this link for some of the recent happenings in this area. Thank you.